So in the last session we discussed about the resonance. Let me quickly revise the concept of resonance once again. For example, if we have a circuit where the circuit consists of passive elements and active elements as like this. So if you observe, out of these circuit elements, some elements are reactive in nature in the sense that its impedance is as a function of reactance, like inductor impedance is jxl, capacitive impedance is minus jxc, where xl and xc are the function of frequency. xl and xc are the function of frequency. And usually what happens in general in the systems is that this supply also has certain frequency, let us say f. If the supply frequency is varying, if the supply frequency is varying, so as a result of the variation in supply frequency, there will be variation in inductive reactance and also variation in capacitive reactance. So due to these variations in the reactance components, there may be some situation that the net reactance, the net reactance at a particular frequency will become zero at certain frequency. That certain frequency let me call as Fr. So this Fr is what the resonance frequency. That means at resonance frequency, the net circuit reactance will become zero. Then if we assume that if it is a series RLC circuit, the total impedance of the circuit is R plus J XL minus XC, right? So R plus J XL minus XC. Now at resonance concept, at resonance, the net reactance in the circuit, that is what this XL minus XC is the net reactance, which will become zero. So the net reactance is what the at resonance frequency, X is what the total reactance, which is equal to XL minus XC will become 0. Now as a result of this net reactance equal to 0, you can observe that the impedance will become R plus J0, which is equal to simply R, That means the impedance is pure resistive at resonance frequency, And one more point also you can conclude here, that the imaginary part of the impedance is equal to 0 at resonance. So this is one more important generalized statement, that at resonance the imaginary part of the impedance is 0, which means that the total reactance of the circuit is 0. If the total reactance of the circuit is 0, then net impedance will become pure resistive. Okay. So now with this basic idea of the resonance, we seen some of the generalized things, that the resonance frequency omega r is equal to 1 by square root LC. This is radians per second. If you need the frequency in terms of hertz, you can write as 1 by 2 pi square root LC. as hedges. Now let us see two more important words, terms which we come across in this concept is quality factor. Quality factor. Quality factor. So the quality factor of circuit is defined as the ratio between two voltages. Let us see what are those voltages is. So usually the quality factor is represented by the letter Q. It is defined as the ratio between voltage across reactive elements. Let me write as like this. Voltage voltage across any one reactive element reactive element. That means we have two reactive elements in series circuit. One is inductor, another is capacitor. So we can take any one, either like inductor voltage or capacitor voltage, to the ratio to the voltage across resistive element resistive element resistive element. Like in series circuit we had, or in generally let me say, like for for series circuit for series circuit. So the quality factor can be written as like this: VL magnitude divided by VR magnitude, or it can also be written as VC magnitude divided by VR magnitude. This is what voltage across any one reactive element, which is inductor or capacitor. And we seen that what is VL in the last session? VL magnitude, I magnitude into XL divided by I into R, or it can also be written as I magnitude into XC divided by I magnitude into R. This we can also write in another way, that XL by R, or simply XC by R. So this can also be further written that XL as omega L by R, XC 1 by omega C. So this can be written as 1 by omega RC. So in this way the quality factor can be expressed either omega L by R or 1 by omega RC. And we know that at resonance, at resonance, at resonance, XL is equal to XC for series circuit, thereby VL magnitude is equal to VC, and as a result of this we will get omega as 1 by square root LC. If we substitute omega over here, we can get this quality factor as omega means 1 by square root LC into L by R for the case 1, this one. So you can try for the second one, just I am doing only the first part. So this L can be written as square root of L square divided by square root LC, square root, fine. So LC into 1 by R, just R, this R I am bringing front side. So as a result of this you can see 1 by R square root L by C. This is what the quality factor in terms of RLC parameters. 1 by R square root L by C. And one more important term is that bandwidth. Bandwidth. Bandwidth is generally represented by BW, and in generalized way it is defined as in this way, that it is the range of frequency which allows which allows in a particular circuit. It is the range of the frequency over which the circuit will allows to pass through it. Generally, we will have this kind of thing that you will understand little later, that we will have some filters like band pass filter or band reject filter or low pass filter, high pass filter, like that. So there you will understand the concept of this bandwidth more detailedly, but as of now just think of that it is the range of the frequency over which allows in a particular circuit, like so. For example, if the circuit frequency is varying 0 to, let us say, something like 10 kilohertz, but circuit is not allowing this entire frequency. Instead of that, circuit is allowing to pass through it only, let us say, some 6 kilohertz to 8 kilohertz, and remaining all frequencies will not be allowed to pass through that particular circuit. Now this amount of the frequency which is allowed to pass through that circuit, we call the range is 8 minus 6 as the bandwidth. So instead of this generalized concept way in understanding this bandwidth, we can think of the known parameters as like this. Bandwidth can be defined as the ratio between resonance frequency to the quality factor. It is the ratio between resonance frequency to quality factor. And we can write these things in many ways, that so you can write resonance frequency is 1 by square root LC, and quality factor you can write as like in many forms. You can write omega L by R or 1 by omega RC or 1 by all these things like R into square root L by C, etc., whatever it is. But in general it is the ratio between resonance frequency to the quality factor. So these are the important terms in this resonance concept. Now let us see one simple problem which illustrate these concepts. So just write down that. So one question, that an RLC circuit consists of R is equal to 1000 ohms and inductance L is equal to 100 millihenry and capacitor C is equal to 10 microfarad. This is in a series RLC circuit. Series RLC circuit. The RLC parameters are given. RLC parameters are given. Next, if a voltage of if a voltage of 100 volts is applied across the combination means RLC combination, across the combination. So determine so what we need to determine is, one is the resonance frequency, let us say FR, and the quality factor Q, and the third one is bandwidth. So let us find these three quickly, and for which we can write FR is equal to, for a series RLC circuit at resonance we can think of XL is equal to XC for series RLC circuit only for series RLC. If it is a different circuit, I will show one example also for that. So the value will change if it is a different circuit, that you need to observe, that I will show with some different example. So this Fr is equal to 1 by 2 pi square root LC. So how much is this value? Check it. So 1 by 2 pi square root L is R is sorry L is 100 into 10 power minus 3 and C is 10 into 10 power minus 6. How much is this value? 1 divided by, just can you check it? 2 pi into square root of, so this 10 power 3 will go away, just straight away 10 power minus 6, right? Yeah. Is there another? No. 159.15 Hz. And what about the second one? This is first one. Just see the second one. Quality factor. You can write in many ways the quality factor. So you can see that how can we write? So it's your wish. You can write omega r by this quality factor. You can write omega r into L by r or directly 1 by r square root LC. It's your wish which form you are using. So I am using here the final form, which is 1 by r square root L by C, which is equal to 1 by 1000 into square root L. L is 100 into 10 power minus 3 divided by C, 10 into 10 power minus, how much is this? 6. Just check it how much we will get. So 100 into 10 power minus 3 by 10 into 10 power minus 6. So square root of the answer divided by 1000. So this is 1 by 10, which is equal to 0.1. Quality factor does not have any units. So it is 0.1. So the third one is bandwidth. So here you should be very careful. Like, so see that. So the bandwidth is defined as omega r by q. So if the omega r is in the radians per second, bandwidth units also in radians per second. If this is in hertz, bandwidth is also in hertz. So that you have to take care. So what is omega r? Omega r by q. So omega r can be written like just let me take. So this as 2 pi f into r divided by q, which is equal to 2 pi into Fr is already known. So I am substituting that 159.15 divided by Q is 0.1. How much is this answer? 2 pi into 159.15 divided by 0.1. This is so 49.68. So approximately this is, so I can say, or let me write as it is, 49.68 units are radians per second. So which is equal to, approximately it can be written as, so 9.999 kilohertz, which is equal to 10 kilohertz approximately. 10, sorry, kilo radians per second, like this. Okay, so this is the generalized concept of the resonance, and which are basically formulations, simple formulations. Now let us see one more important concept with this circuit. Like if it is not series circuit, then how we handle the resonance concept is simple. Like for example, let me take one circuit as like this. So here let us say Vs is equal to 2 cos 1.5 t. Vs voltage is 2 cos 1.5 t, and we have one inductor, so 0.4 Henry, and one resistor as like this, and one capacitor. See that this is not series straight away, or it is not even parallel straight away. Okay, so then still resonance may occur due to some variations in the circuit parameters, either frequency or inductive reactance or capacitive reactance, etc. So here the question is find the value of R, so that so that so that the circuit resonate at supply frequency, at supply frequency. So whenever you see the term resonance, the generalized idea should be that whether it is a series circuit or parallel circuit. These statements are very important for competitive exams. See and observe very carefully. For any circuit, for any circuit that contains at least two two different reactive elements means one inductor, one capacitor, like that, or two inductors, one capacitor, or four inductors, one capacitor. Like we need at least two different reactive elements. One is inductive nature, other is capacitive nature. For example, as like L and C, inductors and capacitors. The circuit must consist of these elements. If only inductors are there or only capacitors are there, resonance does not occur. Okay. For any circuit that contains at least two different reactive elements, example L and C, if imaginary part of the impedance, that is Im of Z is equal to 0, then or let me say that the condition for resonance is that, this is very important, let me write in this way. In any circuit, for any circuit that contains at least two different reactive elements, the condition for resonance is imaginary part of the impedance should be 0. That's all. This is very important. Now you can apply this for even series circuit also. Take the series RLC circuit and see that imaginary part of the impedance equate to 0, you will get the resonance concept. Now in the same way, now see here, apply this concept for this circuit. What we do is that once we see any circuit, first try to find the total impedance of the circuit. Now for this circuit, how much is the impedance? So try to observe that this is, let me write here that this is j omega L equivalent. This is minus j by omega c, or one can write 1 by j omega c. These are the impedances of the reactive elements, and this is resistance as usual. Now what I will do is that try to observe R is in parallel with this capacitor. That combination is in series with the inductor. So now can I write the impedance of the circuit as like this? Z is equal to j omega L, which is in series with rest of the two elements which are connected in parallel. So that is parallel connected combination equivalent impedance is R into 1 by j omega c divided by R plus 1 by j omega c. See, I am writing 1 by j omega c. If j comes to the numerator, it becomes minus j by omega c. That you need to observe. Okay. If you simplify these things by substituting, or just let me take one more step, that j omega L plus, so here in the numerator I will get the R, and in the denominator if this j omega c is multiplied with this, I will get 1 plus j omega into RC. Omega into RC. You substitute all these omega and L. So how we get the omega? Omega is given here. See, this is a 2 cos omega t form. So omega is equivalent to 1.5. And L is given as 0.4, C is given as 0.8. Substitute these things here, and how much we will get? J into omega is 1.5 into L is 0.4 plus R is not known, we need to determine R. So divided by 1 plus j omega is 1.5 and R is not known, C is known, which is equal to 0.8. Now just simplify these things, let us see how much we will get. So 1.5 into 0.4 into 0.4, how much is this? 0.6. So 0.6 j plus R divided by 1.5 into 0.8 is 1.2. So I can write 1. Yeah. So 1 plus j 1.2 R. Now try to see that this is the impedance. Can I say what is the imaginary part and real part in this? So here imaginary part is 0.6, but here it is not clear that, as because things are in the denominator. What we do is that for this kind of things, we rationalize it as like this. So R divided by 1 plus j 1.2 R. Now I will multiply and divide with 1 minus j 1.2 R divided by 1 minus j 1.2 R. So that this denominator will become 1 square plus a plus b into a minus b form, a square plus b square. So that j square will become, so obviously minus minus plus a square minus b square form. Now check it how much we will get. This is 0.6 j plus, let me write the denominator, 1 square is 1, so plus 1.2 square, how much we will get? 1.44 into R square. This is what the denominator. What about numerator? So R minus, just I am multiplying this thing, j 1.2 R square. Now try to observe, it is possible to separate the real and imaginary parts now. Check it how much is the imaginary part. So if I will write here R by 1 plus 1.44 R square is the real part. Next is, if I will take the j to be common, then what is left out here is 0.6, and what is left out in this term is minus 1.2 R square by only this term divided by 1 plus 1.44 R square. This is what impedance. Now what is the resonance condition? Imaginary part of the impedance should be 0 at that location. So circuit will come into the resonance. Now what shall I do in order to get the resistance is that I will write as at resonance imaginary part of the impedance is equal to 0. That means what is the imaginary part here? This portion is what the imaginary part. This is real part. So what we do now? So let us equate the imaginary part to 0. That is 0.6 minus 1.2 r square divided by 1 plus 1.44 r square is equal to 0. Then if we simplify this, just cross verify. So how much we will get is that this is 0.6 into this, then 0.6 into 1.44 into 1.44 is 0. This is place, of course, yeah. So 0.864 r square minus 1.2 r square is equal to 0. Denominator some value, but that is not a matter for us. Then how much we will get this? Check it. 0.6 is equal to, this become negative, so 0.864 minus 1.2 is minus 0.336. If it goes to the right side, it becomes 0.336 r square. Then how much is the r? Just quickly find. So 0.6 divided by this, and this is 1.7, like let me write, r square is equal to 1.785. Am I correct? Just check it. So then square root of this is 1.785 is what the answer, which is R is equal to 1.336 ohms. That means if the R value is this much, the circuit will resonate at supply frequency. What is the supply frequency? 1.5 radians per second. At that frequency it will resonate. Thereby this entire circuit is just behave as a pure resistive circuit. Why? Because imaginary part of the impedance under resonant condition will become 0. As a result, it behave as a pure resistive circuit. Okay, so this is one of the important concept about the resonance. So you should understand carefully this. Once you understand these things, like one important point about the resonance is that whatever may be the circuit, imaginary part of the impedance is 0 at resonant condition. With this statement, you can do many wonders. Okay.